Okay, in this video, I'm going to go through the notes for section 4.1. So we talked about inverses in 2.8. We talked about exponential functions in 4.1 and 4.2. And now we're going to go into section 4.3, which is logs. So the way that logs are related to exponential functions is that they are inverses of each other. And that's why we started out with section 2.8, because that introduced the concept of inverses. So there's more things for you to read right here, but I'm going to start out looking at these tables. So here, I took my function out of function notation, and this is the function y equals 2 to the x. Okay, so I have my domain right here. I have my range right here. This is the inverse function. Notice that the range became the domain, and the domain over here became the range of the inverse. If I try to write this function, the inverse function of an exponential function, look what happens. I switch my x and my y. I have another exponential function, but I can't solve for the y unless I start messing around with natural logs, which is what I'm going to do. So you can ignore this for right now. We'll get back to that detail in a little bit. Okay, so if you were to provide a verbal description of f of x, we would say that f of x represents the value we obtain when we raise 2 to the power of x. So let's look at this. This is 2 to the power of x. That's how I get my y. Okay, so using the thought that an inverse works backwards compared to the original function, can you provide a verbal description of what you think f to the negative 1 of x represents? So it's hard to undo a power. So why don't we first start by switching the x and the y? So you can say that the beginning of the inverse represents having x equal 2 to the y, and I get stuck here. All right, so let's get unstuck. So once again, we're going to start the chapter. I list out the steps that we normally take for finding an inverse. Original function notation, inverse function notation, all a review. Then we say, okay, how am I going to do this? This is what I want. I want to turn this into a y equals equation. This is how you do it. You say, find your base. My base is 2. Write this as log base 2. This is the argument. The argument was the x. Logs equal exponents. There we go. We have isolated the y as the exponent. Your inverse function is y equals log base 2 of x. We're going to do a lot of practice with this. Okay, so if I see right here, it says use your table on the previous page to graph it. So I've graphed it for you in blue. Let's graph f to the negative 1 of x. So I'm going to see if I can turn on this little pencil feature. And let's see what I want to do. All right, so I'm okay. So let's plot some points. So I'm going to change my color away from the blue to red to do the inverse. Okay, so I see a point right here, and that point is 2, 4. So let's find 4, 2. 1, 2, 3, 4, 1, 2, right there. So I put a little red dot right there. Then look at this point. This is 1, 2, so I need 2, 1, 2, 1, right there. I put that little point. Here's another one. This is the point 0, 1. I need 1, 0, right there. Okay, that's going to pretty much do it for me. I'm now able to plot this. So look what I'm going to do. I'm going to try to drag this kind of through here. It's going to be rudimentary, but you get the sense of it. This is going to come down there. This is going to go up there or out there. And that's a very poor drawing, but It is what it is with this technology. So what I'm seeing is that my original function is asymptotic to the x-axis. My inverse function is asymptotic to the y-axis. My original function goes up along the y-axis. My inverse function goes out along the x-axis. That seems like inverse behavior, so I'm happy with that. Domain and range, you should be able to see from the graph. Notice that the domain of the original function becomes the range of the inverse. Okay, nothing new there. And just to reinforce one more time, a little bit of this, y equals log base 2 of x. The y is the exponent, the base is 2, and the argument is the x. Okay, let's see if I can go down to my next page. Okay, let me see if this is going to let me do this. So hang on, I'll be right back. Okay, so I just lowered the page a little bit, and you can see that this is exponent, this is base, this is argument. We're going to do a lot of practicing with this. Okay, so let's go down a little bit. Here we go. In more general terms, we're going to do the following. If you try to create the inverse, and this is what you got stuck with, the way you get unstuck is you say, what's the base? The base is b. The base is the base of the log. Then you say, what's the argument? Here's the argument. The argument goes behind the word log, and logs equal exponents. So logs equal exponents. Where's your exponent? There it is at y. That's how you switch it. Make sure you are comfortable with this. These two equations are completely equivalent. So you can use one in place of the other as appropriate. Okay, so let's convert from log form to exponential form. If I give you log form and I want exponential form, first thing you ask yourself is, what is your base? Your base is this little number. Put the base down. Logs equal exponents. Put the exponent up. Then your remaining number is the argument. The argument is found behind the log term, and it goes on the other side of the equal sign of the exponential form. Okay, let's try another one. Log base 4 of 16 equals 2. What's your base? 4. What's your power? Logs equal exponents or powers. It's 2. Equals, what's your argument? 16 is the argument. 16 goes out here. Okay, a word about this. This is the last time pretty much you're going to see log base 10. If the base is 10, you'll just see it written as log 10. The 10 base is implied. So let's take this expression, log base 10 of 10 equals 1. Write it in exponential form. What's your base? It's 10. What's your exponent? It's 1, because logs equal exponents. Equals, what's your argument? The argument is the number behind the word log. Done. Okay, another word about this. You will not see log base e written like this. Whenever the base is e, we write ln, which stands for natural log. Okay, so I replace log base e with ln, and then I continue writing it. Okay, what's your base? My base is e. What's your exponent? My exponent is 0 because logs equal exponents. What's your argument? It's 1. This equals 1. Okay, last one. What's your base? 3. What's your exponent? Since logs equal exponents, it's -2. What's your argument? 1/9. Done. Okay, so let's keep moving. So what if I ask you to take it from exponential form to log form? You've got to be able to do it both ways. What's your base? 10. That tells me I just write the word log. What's my argument? 1,000. That goes here. What do logs equal? They equal exponents. Here's your exponent 3. What's your base? My base is 2, log 2. What's my argument? My argument is 1/2. This says 1/2 equals, what do logs equal? Logs equal exponents. Where's my exponent? -1. Okay, so this is base E. So I'm not going to write log base E. I'm going to write natural log. What's my argument? It's 7.389. What's my power or exponent? It's 2. What's your base? My base is 9, log base 9. What's my argument? My argument is 27. Put the 27 behind the word log. And it equals exponents. What's my exponent? 2/3. So make sure you can do this because this is essential. You've got to be able to create the equivalent log form from the exponential form and the equivalent exponential form from the log form. Okay, finding common logs and natural logs. So once again, I say in this verbiage that log base 10 is not going to have a 10 anymore, and natural log or log base E will not have a log E anymore. They will be written instead as log with no 10 and ln with no E, respectively. So make sure you're comfortable with that and that you recognize them. Let's try to solve some things. We're going to solve for x, and you can say, well, we don't have an x. Well, you're going to set each of these logs equal to x. And now our job is to solve for the x. What are the x's? Well, the x's are all the exponents because logs equal exponents. So I can't solve for it here. I don't know what this equals. I'm going to write it in exponential form. So my base is 2. 2 to the x equals 16. Make sure you can get that. Now that seems like a reasonable thing to solve. Think about how many times you're going to take 2 to get 16. And I wrote it out here. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So x, which is the power, must be 4. Next one. Write this in exponential form. Base is 5. Logs equal exponents. Exponents is x. And that's going to equal the argument. The argument is 1/25. Okay, so what I didn't write was that 1/25 equals 5 to the -2. So therefore, 5 to the x equals 5 to the -2. Since the bases are the same by unique base, we can set x equal to -2, and that's what I have for my answer. Okay, look at this one, natural log of e. And you can stop this video at any time and go back and think about this some more. Natural log of e equals x. Okay, change the form. So what's your base? My base is e. What's your exponent? My exponent is x. What's your argument? That's also e. So look what I find. If there's no power here, then you can put the 1 where you have it right here, where I put it right here in purple. So x equals 1, because your bases are the same by unique base. X equals 1 is our answer. Last one here, log base 10 this is, of 100 equals the x that I'm looking for. So what's your base? It's 10. What's your exponent? Logs equal exponent. It's x. What's your argument? Equals 100. So isn't it true that 10 to the x equals 10 to the second, which is 100, therefore x equals 2. And that's what I have right there. Okay, so let's keep going since we're doing so well. Now this is the easiest part ever. Set your mode on your calculator to 4. Okay, so go down to where it says float and change the float to 4. You're looking for the word mode. It's across the top. So you're going to say, in your calculator, you're going to type in the word log, which is on the left-hand side towards the bottom of those keys. Then type in 1837 and give me the answer to 4 decimal points. You should be able to get each of these. So you want to know where the log key is and where the natural log key is. Okay, log is base 10, natural log base E. Okay, so we're going to talk about some graphing here. And what you can see I did, you have the exponential growth function, and that's growing exponentially, so quickly. And then what you're going to notice is when you take the inverse, it's going to be a slower growth. Okay, so those are inverse functions. So be able to recognize the way that logs work and the way that inverses work. There's some common points. So 0, 1 is always on the exponential growth curve, and therefore 1, 0 will be on the natural log curve. They are reflections over the line y equals x, and here are their characteristics. Make sure you can understand them. Okay, so here's two important takeaways. The fact that the domain of the parent logarithmic function is 0 to infinity leads to the very critical conclusion that you can only take the logarithm of a positive number. Okay, so you can't take a log of a 0 or of a negative. That is huge. Okay, so notice that a horizontal shift of the parent function will lead to a horizontal shift of the vertical asymptote as well as the underlying domain. So the domain and the vertical asymptotes will travel with our shifts. Okay, so that's just good to know. Okay, we're going to skip this section. I did write some things down, but we're going to skip it and come down to this. Okay, so if you want to find the domain of a logarithmic function, number one thing, you cannot take the log of a negative or a 0, and that's based on the graphs we just talked about. Okay, so how are you going to determine the domain of each of these logarithmic functions? There are two ways, and I would say you're going to find the graphical method easier, but we'll do both. Okay, algebraically, you can't take the log of a 0 or a negative. So therefore, this expression right here, the 2x minus 3, also known as the argument, has to be greater than 0. So when it's a line, it's very simple to do it algebraically. This is going to tell me that 2x minus 3 is greater than 0. Therefore, 2x is greater than 3, and therefore x is greater than 3 halves. Remember, if you divide or multiply across the inequality sign by a negative, it flips the inequality sign. So put that in the back of your mind. So I'm getting a domain of x is greater than 3 halves, which in interval notation, which is what we use, you would write like this. Now, another approach that I think is really very, very clever. Whatever this function is, plot that function. And you can plot it by using your transformations. Okay, so this is a vertical stretch of a line and then down 3. That's where I graph this. Since this is your y, right? This is your argument, and the argument is going to equal the y, and I can't take the log of a negative number. That means my y value, which are down here, can never be negative and be involved in my domain. So the yellow cannot be included. So look where I'm starting. I'm starting at 3 halves and going further and further down the x-axis. So my domain is once again 3 halves to infinity. Okay, I have to eliminate all the yellow because that's where my y values are negative, and I can't have any negative y values because that's going to make this negative, and this can't be negative and it can't be 0. Okay, so we've got a couple more to think about. Okay, look at this next one. Log base 5 of x squared minus 3x. So algebraically, I can say this guy can't be, or has to be, greater than 0. So what I did was I factored it. Okay, so now this gets a little bit complicated. This is what's called a sign chart. So what I do is I take the value that makes either the x equal to 0 or the x minus 3 equal to 0, and I place them here and here. So 0 makes x 0, and x minus 3, so 3 is going to make that 0. So I'm not going to have to, that's going to be my numbers I'm not going to include because this cannot equal 0, right? So think about numbers to the left of 0. What if I plug in a -1? This is going to be -1 times a -4. That's a positive. Put a positive here. I can have numbers that are down this way. Pick a number between 0 and 3. I pick 1. 1 times a -2 is going to be less than 0. It's going to be negative. I can't use it. Put your negative here on the sign chart. Then pick a number to the right of 3. I pick 4. That's going to be 4. That's going to be 1. 4 times 1 is greater than 0. Yep, I can use it. So my domain is going to be numbers from, oh, I should have done this. Let me think about this for a second. Okay, let me think about this for 1 second. Yeah, I have to make a correction here, and you can probably see the correction. Let me just see if I can change this. I'll keep this red. This should be -infinity to 0. So make this a 0, and then this is going to be then from 3 to infinity. Let me fix this one while I'm at it. So this is going to be 0 right here. So excuse this typo. Okay, so this is how you do it with the sign chart. Now, you're not really that great with sign charts because I just taught you it 2 seconds ago. So let's instead talk about the graphical analysis. Can you graph this? Well, this is a parabola that's been transformed. So the easiest way to graph this is to do the following. Get your 2 roots. They are 0 and 3. This is an upward facing parabola, so here is my shape. I know my roots are 0 and 3. Where can my y's not be? My y's cannot be negative, so I'm going to exclude these negative. So what am I going to, oh, I have to do this again. What am I going to do? I am going to draw in, because it didn't hold, my zeros where they should be. So remember, this is going to be 0, so make your correction because this is going to go back to be uncorrected as soon as I turn this thing off. Okay, make that 0. Okay, so you can have all this area, which is -infinity up until 0, and you can have this from +3 all the way to infinity. That's your domain, and that's how I handled it. Okay, so for this one, I think the algebraic explanation is very confusing, so I'm going to avoid that totally. I'm going to instead graph this in my graphing calculator. I get this shape. What I did was I highlighted in yellow all the y values that are below the x-axis because I cannot have them. So where can I be? I can be from here up to here. So I can start at -3, non-inclusive, and go all the way to 3, non-inclusive, and that will give me values that are greater than 0, which is the requirement for this log to work. Okay, so that's a couple of things there. So I'm going to turn this off again, and it's going to change that drawing back, I think. Yep, it did. Okay, so you've already made the corrections, so you are good. Okay, let's do this last one. I'm going to ignore this algebraic example too, and I'm going to go with the graph. I think the graph is a much easier way to understand it. So look at this absolute value function. What I've done is I've taken the absolute value function and I've shifted it down 2. So when I shift it down 2, what happens is I am shifting the vertex down to here, which makes the roots -2 and 2. Okay, if I shifted it down to 1, the roots would have been -1 and 1, but shifting it down 2 changes these to -2 and 2. So where are the y values negative? Where I have the yellow, the highlighted. So what values can I use? I can use from negative infinity up to negative 2, not inclusive, and from 2 to infinity. Okay, those are the y values that are permissible, or those are the x values that generate the y values that are permissible, and that is my domain. Okay, so I'm going to say do the graphical approach. We're going to use transformations to do the graphical approach. Clearly a line is the easier one to use. So, whenever you have a line, that's going to be very easy to graph. It's going to be very easy to look at where the y's are generated to be negative, and those are the x's that generate those negative y's that are excluded from your domain. Okay, so this marks the end of these notes. You should be able to do the 4.3 homework now.